Welcome to a new session of the virtual seminar of Geometry with Symmetries. Today's talk will be, the speaker will be Alberto Rodríguez Vázquez from Université Libre de Bruxelles, and he will talk about totally geodesic submanifolds in homogeneous nearly Kähler 6 manifolds and their G2 cones. Thank you, Alberto.
Okay, thank you very much. Thanks, Emilia, for the invitation. It's a pleasure to speak at this seminar. And today I will be talking on a joint work with Juan Manuel Lorenzo Naveiro, who is a grad student from Universidade de Santiago de Compostela and is finishing his PhD this year. So yeah, the title of my talk is Totally Geodesic Submanifolds in Homogeneous Nearly Kähler 6 Manifolds under G2 cones. And this is the same title of a work where we classify totally geodesic submanifolds in nearly Kähler 6 manifolds and, well, in nearly Kähler 6 manifolds which are homogeneous under G2 cones that can be read in archive. So first of all, let me tell you about the structure of this talk. I will start by introducing totally geodesic submanifolds. Then I will explain some facts about nearly Kähler 6 manifolds and their connection to G2 geometry. Later, I will talk about totally geodesic submanifolds in naturally reductive homogeneous spaces. The reason for this is that the nearly Kähler homogeneous 6 manifolds that we will consider fall into this class of homogeneous spaces, those which are naturally reductive. Then I will state our classification result. And finally, I will talk about totally geodesic submanifolds in Riemannian cones, where we also have developed some structure results in the general case. So let me start by telling you a little bit about totally geodesic submanifolds. So we are going to consider an ambient space called M, which is a Riemannian manifold. And we are going to consider a submanifold sigma on it. And we say that a submanifold is totally geodesic in M if every geodesic of sigma is also a geodesic of M, of the ambient space. This definition is equivalent to the vanishing of the so-called second fundamental form that measures the complexity of the extrinsic geometry. So totally geodesic submanifolds are from this point of view the simplest submanifolds that we can consider, those with vanishing second fundamental form. And through this talk, I will denote totally geodesic submanifolds in this fashion, sigma subset TGM. Some examples of totally geodesic submanifolds are in this slide. So for instance, in Euclidean spaces, totally geodesic submanifolds are affine subspaces. In round spheres, they all can be recovered by taking intersections of an affine subspace passing through the center of the sphere with the sphere itself. And similarly, if we take the hyperboloid model of the real hyperbolic space, we can get all totally geodesic submanifolds by taking intersections of affine subspaces as well. All these examples here in these pictures are fixed point sets of certain isometries. Indeed, in general, if you have a Riemannian manifold and you take an isometry, a fixed point set of an isometry is always totally geodesic. However, the converse is not true. Okay, so the existence of isometries is usually very linked to the existence of totally geodesic submanifolds, and this is one of the reasons why we want to study totally geodesic submanifolds in very symmetric situations when you have lots of isometries. Okay, so what's the motivation behind studying totally geodesic submanifolds? Where One of the main motivations is that totally geodesic submanifolds arise in a wide variety of contexts. So, for instance, in geometric analysis, we have these Alexandrov type theorems. So, basically, for me, an Alexandrov type theorem is a theorem that proves rigidity of compact hypersurfaces with constant mean curvature which are embedded in some ambient space. So for instance, in Euclidean spaces, those kind of hypersurfaces are always geodesic spheres. The same happens for hyperbolic spaces or even for round spheres under some appropriate assumptions. And the technique to prove this sort of theorem is basically it was basically provided by Alexandrov, who proved or who developed the so-called reflection method that consists in reflecting a hypersurface against itself with respect to a totally geodesic hypersurface. So when you have totally geodesic hypersurfaces, you can perform this reflection method to prove this sort of theorems. Another place where these totally geodesic submanifolds appear is in the study of manifolds with positive curvature. Here we have the connectedness principle proved by Wilking, and this is one of the main tools in the study of manifolds with positive sectional curvature. The connectedness principle provides us with some topological abstraction for the existence of totally geodesic submanifolds. So the idea here is that if you have a Riemannian manifold of dimension n and a totally geodesic submanifold of codimension k, and this ambient space is positively curved, then the embedding of this totally geodesic submanifold must be an m minus 2k plus 1 connected map. So the topology of the ambient space is obstructing the topology of the possible totally geodesic submanifolds. Another context where the totally geodesic submanifolds appear is in the study of arithmetic lattices, which is an area that has more to do with arithmetic geometry, or if you want, even number theory. So in a recent work, Bader, Fisher, Miller, and Stover prove that if you have a lattice in a real hyperbolic space, so I mean a lattice of the isometry group of a real hyperbolic space, then this lattice is going to be arithmetic if the resulting quotient has infinitely many totally geodesic submanifolds. So even in this study of arithmetic lattices, which are those lattices, I am not going to give you the precise definition of this because it's complicated, but intuitively this just means that the points of this lattice have like sort of integer coordinates like SL2C inside SL2R. Determines by the properties of the totally geodesic submanifolds associated in the quotient this arithmetic property. So it's also an example where totally geodesic submanifolds appear in a very natural way. And one possible approach to understand more about totally geodesic submanifolds is to perform classifications in special situations or in special classes of ambient spaces. So in our case, we are going to consider spaces with lots of isometries, with lots of symmetries, because this makes the study of totally geodesic submanifolds, the theory of totally geodesic submanifolds in these spaces, way richer. Apart from that, we are also going to consider spaces with special geometric structures because we are also interested on the interaction between totally geodesic submanifolds and these special geometric structures. So this is a topic, the classification of totally geodesic submanifolds, that has been extensively studied for symmetric spaces. In symmetric spaces, an important invariant is the rank. The rank can be defined as the homogeneity of the isotropy representation of a symmetric space. Another more geometric definition, if you want, is the following: the rank of a symmetric space is also the maximal dimension of a flat and totally geodesic submanifold. And the classification for rank 1 symmetric spaces is a classical result obtained by Wolf in the 60s. So rank 1 symmetric spaces are up to quotients, the spheres, the complex projective spaces, the quaternary projective spaces, and the Kähler projective plane, and also their duals, so the associated hyperbolic spaces. And let me just remind you that for studying totally geodesic submanifolds in symmetric spaces, we only have to do it in the compact or in the non-compact case, because then we can pass all we know about totally geodesic submanifolds in one setting to the dual of it by duality. So in rank 1, the classification is well known. In rank 2, this was a problem that was studied by Chen and Nagano in the 70s, but there were certain omissions in their classification that were found by Sebastian Klein 10 years ago in a series of papers. Then more recently, we also have the computation of index. So the index of a symmetric space is the smallest codimension of a proper totally geodesic submanifold, and Jürgen Bern and Carlos Olmos computed the index of every symmetric space in a series of papers. And more recently, in my PhD thesis, together with Andreas Kollross, we classify maximal totally geodesic submanifolds in exceptional symmetric spaces. The reason of why we restrict ourselves to the maximal case is that usually it's enough to list maximal totally geodesic submanifolds and then recursively at each stage list the maximal totally geodesic submanifolds of the maximal totally geodesic submanifolds and so on to get a complete list. Okay, so that is for symmetric spaces, but for homogeneous spaces that are non-symmetric, there has also been some results. So for instance, we have some structure and partial results by Patrick Eberling in the 90s, where he classified or he studied totally geodesic submanifolds in generalized Heisenberg groups. And also more recently, together with Carlos Olmos, we classify totally geodesic submanifolds in Hofberger spheres. By Hofberger spheres, we mean the total space of a Hopf vibration over the complex projective space, over the quaternary projective space, or over S8, the so-called octenary Hopf vibration, where we rescale the metrics of the total space in the directions of the fibers of the Hopf vibration. This allows us to consider many different homogeneous metrics, and here we can see some new phenomena, some new classes of examples and different behaviors that cannot occur in symmetric spaces. So this also motivates the study of totally geodesic submanifolds in other homogeneous spaces, because as we will see, there are certain differences with the more classical, let's say, setting of symmetric spaces, where totally geodesic submanifolds are especially well behaved. So now I'm going to talk about Nierli-Kähler geometry in dimension 6 and its connection with G2 geometry. And let me start by telling you that an almost Hermitian manifold is said to be Nierli-Kähler if the tensor nabla J, where nabla denotes the Levi-Civita connection, is skew-symmetric. So Boutroux classify homogeneous Nierli-Kähler 6 manifolds. We have these 4 spaces. Here we have S6. Here X6, of course, is equipped with round metric because this homogeneous space is isotropy reducible. Here SU3 is acting with its standard action on C3. via the isotropy representation. So there is only one possible metric up to scaling, so it has to be the round one. Then we have the flag manifold. Then we also have this complex projective space, which is not equipped with the Fubini study metric. And then also this product of spheres, which again is not the standard product of spheres. It doesn't have the standard product metric. Well, these two spaces, the flag manifold and CP3, are examples of twistor spaces. They are fibering over CP2 and S4 respectively. And yeah, this is going to give this submersion structure is going to give it's going to provide some how to say, some structure also for our totally geodesic submanifolds, because this S3 cross S3 also can be understood as the total space of a certain submersion, a homogeneous fibration as well. Well, so these were the homogeneous nearly Kähler 6 manifolds, but there are also examples of inhomogeneous nearly Kähler manifolds happening in dimension 6. These were discovered by Foscolo and Haskins, and so far we only have examples in S6 and S3 cross S3. These are nearly Kähler structures of homogeneity 1. Well, nearly Kähler 6 manifolds are very linked to this other interesting class of geometric structures, which are G2 structures. Recall that a G2 manifold is a Riemannian manifold for which its holonomy group is a subgroup of G2. And this can be rephrased via the following equivalent condition. So a G2 manifold is a Riemannian manifold for which there exists a parallel thief form stabilized by G2. Okay? So how these two geometric structures, the nearly Kähler and the G2 structure, interact? Well, if we have a nearly Kähler 6 manifold, they are automatically Einstein, okay? And we can consider the cone over these nearly Kähler 6 manifolds. So we consider the product of R cross M, and we equip this product with this metric. And now Bryant proof that if you have the flag manifold and you consider the nearly Kähler metric on it, and you consider the cone over this flag manifold, this has holonomy equal to G2. And this was indeed the first example. Indeed, it was a non-complete example, but it was the first example of a manifold with holonomy G2. We have to understand a little bit the context of this discovering. The thing was that you have this list of possible 7 of possibilities for the holonomy group of a Riemannian manifold that was not irreducible, not locally symmetric to a symmetric space, and complete and simply connected. In this case, its holonomy is one of the groups appearing in Berger list, and at that point, G2 and spin 7 were not known to happen as the holonomy group of a Riemannian manifold. So this was such a discovering at the time. More later, Baer proved that this was actually a more general phenomena. If you have a nearly Kähler 6 manifold, which was not the round sphere and simply connected, then the cone over it always has holonomy equal to G2. So to start with a nearly Kähler 6 manifold always give us the possibility to create manifolds with holonomy G2, the non-complete manifolds, okay, because they are cones. That's important. Okay, and nearly Kähler and G2 manifolds have some special types of submanifolds. So, yeah, when you have a almost Hermitian space, some natural classes of submanifolds are totally real. Those are submanifolds for which the almost Hermitian structure sends the tangent space at each point to the orthogonal complement, and those which are almost complex. This means that the tangent space is left invariant by the almost Hermitian structure at each point. There is also some kind of intermediate notion between totally real and almost complex. So let me define it at the linear algebra level. So let's consider a real subspace of Cn. Then we can define what is called the constant Kähler angle of a subspace. So this is defined as follows. We take a vector in our subspace V, and now we take I of B. V is a vector there, and we take the orthogonal projection of this vector. Well, if this is equal to the cosine of phi squared, dot the square norm of B for every vector in V, then we say that V has constant Kähler angle phi. And this notion recovers totally real and almost complex submanifolds, because when the Kähler angle is equal to pi over 2, this means that I of B is sent to the orthogonal complement, and when the Kähler angle is equal to 0, this means that IV belongs again to the subspace V. So they are invariant under the almost Hermitian structure. But in between, we have some conditions, let's say between 0 and pi over 2, for subspaces which are not almost complex nor totally real. So some good class of almost Hermitian manifolds is that of Hermitian symmetric spaces. These are symmetric spaces which are also Kähler. And in this regard, we can try to compute the possible Kähler angles of totally geodesic submanifolds in irreducible, this means irreducible, Hermitian symmetric spaces of rank R. So for rank equal to 1, we just have one possibility, the complex projective space, or the same, the complex hyperbolic space, which is going to be the same for the study of totally geodesic submanifolds. And in this case, the only possibilities are 0 or pi over 2. Because we only have totally geodesic CP case or totally geodesic RP case, which have Kähler angle equal to 0 or pi over 2. They are either almost complex or totally real. So in this case, they are very well behaved with respect to the almost Hermitian structure. However, if we go up in rank, if now we consider a Hermitian symmetric space of rank 2, we can consider, for instance, the oriented Grassmannian in R5 of two planes. So in this case, Sebastian Klein observed that there were examples of totally geodesic submanifolds that were not well behaved with respect to the Kähler structure, because there are some totally geodesic spheres of dimension 2 where the Kähler angle is neither 0 or pi over 2, is arc cosine of 1 over 5. Indeed, in my PhD thesis, I observed that in higher rank, and let me say that so far the classification of totally geodesic submanifolds of symmetric spaces of high rank, this means higher or equal than 3, is a very open problem. I observed that the angles or let's say it in another way, the arccosine of every rational number in 0, 1 can be realized as the Kähler angle of a totally geodesic submanifold in a Hermitian symmetric space of large enough rank. Okay, so we have many possible Kähler angles realized when we consider higher rank Hermitian symmetric spaces. So something that I don't know is what happens with the other inclusion. So this will mean that all the possibilities of totally geodesic submanifolds with constant Kähler angle in a irreducible Hermitian symmetric spaces have a Kähler angle whose arco-cosine is a rational number. And this will be a very interesting rationality property that possibly will be related with the structure of the Lie algebras underneath. That will be very interesting to study with more detail. But this motivates the study of the behavior of totally geodesic submanifolds of nearly Kähler manifolds with respect to the nearly Kähler structure. And in this case, we will observe that totally geodesic submanifolds in nearly Kähler six manifolds, which are homogeneous, are well behaved with respect to this nearly Kähler structure. They are going to be either totally real or almost complex. Okay, we can do something similar for G2 manifolds. Now we also have some special classes of submanifolds. We have associative submanifolds, which are those which are calibrated by the G2 structure phi. So recall that a calibration is a differential form which is closed and that has commas 1. This is this property here. So we plug unit vectors, and the result of this is always a number which is less or equal than 1. In this situation, we say that a submanifold of dimension k is calibrated if its volume coincides with the restriction of the calibration to the tangent space. Okay, so associative submanifolds are those calibrated by phi, and co-associative submanifolds are those calibrated by the Hodge dual of phi. And there is a connection between special submanifolds in nearly Kähler geometry in dimension 6 and special submanifolds in G2 manifolds. When we consider almost complex or J-holomorphic curves in a nearly Kähler manifold of dimension 6, then we can induce an immersion in the cone over these manifolds. And the cone will be associative, and vice versa. If the cone over a submanifold of a nearly Kähler manifold is associative, then the underlying submanifold in the nearly Kähler ambient space of dimension 6 was almost complex. And we have a similar relationship for Lagrangian submanifolds. In this case, the cones will be co-associative and vice versa. The link of this map, of this co-associative immersion, will be Lagrangian submanifolds. Okay, so another goal in this project is to understand the behavior of totally geodesic submanifolds of G2 manifolds with respect to the G2 structure. Okay, so now I can tell you a little bit about naturally reductive homogeneous spaces and totally geodesic submanifolds. But first let me tell you a little bit about some things that we have to take care of when we are working in the homogeneous setting regarding totally geodesic submanifolds. So we are going to consider isometric immersions in a real analytic manifold. Homogeneous spaces are real analytic. The reason why we want to study totally geodesic submanifolds in analytic Riemannian manifolds is that in the analytic setting, we are allowed to make some sort of analytic continuation of our totally geodesic immersions. So we can consider, let's say, inextendable totally geodesic immersions. And also, we want to allow self-intersections. This is some phenomena that was not occurring in symmetric spaces. In symmetric spaces, totally geodesic submanifolds are always orbits of some isometric action, and therefore they will be automatically injectively immersed. But for homogeneous spaces in general, it could happen that we have totally geodesic submanifolds which allow self-intersections. Indeed, we will present what we believe is one of the first examples of a totally geodesic immersion which has self-intersections in a simply connected homogeneous space. Okay, so in this setting, we will say that a totally geodesic immersion is an immersion for which the composition with geodesics is a geodesic of the target space for every geodesic of the domain, okay? And it's important in this setting to consider an induced map on the Grassmann bundle of the tangent space, which we will denote by F tilde. So for every point on the domain, we consider the image of the tangent space under the differential map. So this gives us an immersion of our totally geodesic submanifold, let's say, into the Grassmann bundle. Moreover, one can prove that this immersion is entirely determined by the image at just one point. Okay. So Hermann also gave a criteria that allows to detect when a totally geodesic submanifold is tangent to a certain subspace. And this can be rephrased for analytic Riemannian manifolds via the following condition involving derivatives of the curvature tensor. So we say, or it holds that a totally geodesic or a subspace is going to be tangent to a totally geodesic immersion if and only if this subspace is invariant under all covariant derivatives of the curvature tensor. So something that we also have to take care when we are considering or when we are classifying totally geodesic immersions is the following. We have to take care of two possible redundancies. One redundancy appears when we consider different domains which are isometric. So we will say that two isometric immersions are equivalent if there is an isometry from one domain to the other that makes this diagram a commutative diagram. So we have to take care about reparametrization of domains, and the idea to take care of this is to consider totally geodesic immersions up to equivalence, up to this notion of equivalence that we just defined. This is something that we have to take care when we consider totally geodesic submanifolds that are not embedded. Usually the case was that all totally geodesic submanifolds were embedded. So when we were studying the classification, we didn't really have to care about these subtleties. Another subtlety is that we can take covers. So for instance, we can consider the following situation. Imagine that we are considering the totally geodesic immersion of RP2, the real projective plane, inside RP3. This is an embedding. But now we can take the universal cover of RP2, S2, and compose this to get an immersion, and now it's not an embedding, of S2 in RP3. And this will be totally geodesic. However, this is not a honest totally geodesic immersion. We have done some kind of trick by considering this universal cover. So we want to avoid these redundancies. In order to do so, we are going to consider compatible immersions, which will cancel these redundancies. So a compatible totally geodesic immersion is an immersion for which this map F tilde here is injective. So for instance, embeddings, totally geodesic embeddings, are automatically compatible totally geodesic immersions. So as you say, this is something that we don't have to care when we have all our totally geodesic submanifolds embedded. So what we are really considering here when we classify totally geodesic immersions is the classification of compatible totally geodesic immersions up to equivalence. Okay. So what about the ambient spaces that we consider? These are or this will fall into the class of naturally reductive homogeneous spaces. So for a Riemannian homogeneous space, we can consider its reductive decomposition. This is a splitting of the Lie algebra into subspaces K plus P. And now we say, or we identify P with the tangent space at M of M at O via Killing vector fields. And we say that M is naturally reductive if the Lie exponential map, which is this one here, and the Riemannian exponential map agree, okay? So examples of naturally reductive homogeneous spaces are symmetric spaces, homogeneous neatly Kähler manifolds, and so on. And the curvature of the Levi-Civita connection in this context is provided by this formula. Let me recall that the curvature is essential to understand totally geodesic submanifolds because of this theorem by Hermann. Also, let me recall you that, this theorem by Hermann is just a global extension of a theorem that was first proved by Cartan, who gave a local analog of this statement proved by Hermann. Okay, so another connection, apart from the Levi-Civita connection, that we can consider in a homogeneous space is the canonical connection. For a naturally reductive homogeneous space, the canonical connection has this expression at the base point O, and then we can expand the definition of the canonical connection at every point, extended by G invariance. The curvature of the canonical connection is given by this formula here. And something that is interesting is to consider or to compare these two connections, the Levi-Civita connection and the canonical connection, and this will give us a tensor that we call the difference tensor. The difference tensor will be 0 exactly when our homogeneous space is symmetric, okay? So, as I said, a symmetric space satisfies that the difference is 0, the difference tensor is 0, the curvature coincides with the canonical curvature, and also the derivatives of the curvature tensor are 0. So then, by using the theorem that I mentioned before by Hermann, totally geodesic submanifolds are characterized by this property. They are going to appear as the subspaces which are invariant under the curvature tensor. We only have to check that condition because all the other covariant derivatives of the curvature tensor vanish. But the curvature tensor for symmetric spaces is equal to the canonical curvature tensor, and this has a much simpler expression that can be understood in terms of Lie brackets. So we only have to care about subspaces which are invariant under this triple bracketing condition, and these are the so-called Lie triple systems. So the problem of classifying totally geodesic submanifolds in symmetric spaces is equivalent to an algebraic problem, which is the classification of Lie triple systems. However, this is a very involved problem, a very involved algebraic problem that has only been solved until or for symmetric spaces of rank less or equal than 2. So in this article, we consider a generalization of Lie triple systems or totally geodesic submanifolds that are induced by Lie triple systems in naturally reductive spaces that we call the invariant totally geodesic submanifolds, and this can be characterized by the following conditions. So in a naturally reductive homogeneous space, all these conditions are equivalent. The existence of a totally geodesic d-invariant submanifold, the fact that our subspace V is invariant under the curvature and the difference tensor, the fact that V is invariant under the canonical curvature and the difference tensor, or the fact that there is some subgroup of the group acting transitively and isometrically on our homogeneous space, whose Lie algebra splits well with respect to the reductive decomposition, and such that the submanifold sigma is an orbit, a totally geodesic orbit of this subgroup S. So all these conditions are equivalent, but the point here is that not all totally geodesic submanifolds in a naturally reductive homogeneous space are D-invariant. So the problem of classifying totally geodesic submanifolds in a naturally reductive homogeneous space is not fully an algebraic problem. We have to consider higher order derivatives of the curvature tensor. And we know that we only have to consider a finite amount of derivatives, but this number of derivatives of the curvature tensor can be very large. So now let me state...
Alberto?
Yes, sorry?
Can I ask you a question about the
Yes,
previous
sure.
slide?
Sure.
Is there a way to measure whether the invariant are more than the non-D-invariant totally geodesic submanifolds?
Okay, so this is a very interesting thing. So something that we have came up in this work is that all the maximal examples that we have are D-invariant. So the only examples that are not D-invariant that we know so far, and that I know so far indeed, because I in other spaces the situation was. In other naturally reductive homogeneous spaces that I have studied, the situation was always the same. All totally geodesic submanifolds that were maximal were automatically D-invariant. So I don't dare to conjecture that this is probably the case, but this could be the case. There could be. So answering your question, yeah, it could happen that most of totally geodesic submanifolds were D-invariant, and that this property just fails when you consider some or certain non-maximal totally geodesic submanifold. So this will be really interesting to further study, to try to prove when in a homogeneous space all totally geodesic submanifolds, maximal totally geodesic submanifolds are D-invariant. So yeah.
Okay, thank you very much.
Yeah. So let me now move to state. I am not going to tell you about the proofs of our classification, but they are based on some methods that we developed for studying totally geodesic submanifolds in naturally reductive homogeneous spaces, and in the study of higher order derivatives of the curvature tensor and the isotropy representation of these spaces. So I am going to tell you only about the main results, so the classification results. So here we have the totally geodesic submanifolds of the nearly Kähler CP3, and we have that, as I mentioned before, that they are well behaved with respect to the nearly Kähler structure. They are going to be either Lagrangian or J-holomorphic. So we have these three J-holomorphic curves, and I want to stress this last one, which was a new totally geodesic J-holomorphic curve that we found that is not well behaved with respect to the twistor vibration. So this means that it doesn't split as at each point as a vertical subspace plus a horizontal subspace. Is not well positioned. Indeed, it's an orbit of a subgroup, a SU2 subgroup inside SP2, which is maximal. It's a maximal subgroup and is induced by the four-dimensionally reducible representation of SU2. In the flag manifold, we have a very interesting example, this RP2. This RP2 is not extrinsically homogeneous. It's not even an orbit of an isometric action. Indeed, it's not even injectively immersed. This is an example of a totally geodesic submanifold which has self-intersections. And up to our knowledge, as I said before, this is the first example of a totally geodesic submanifold with self-intersections in a simply connected homogeneous homogeneous space. And this is kind of surprising because in a homogeneous space, for geodesics, when you consider geodesics, geodesic loops are always closed geodesics. So this means that they cannot have self-intersections. And this is something that is easy to prove. But if you go higher in dimension, if instead of considering geodesics, now you consider totally geodesic surfaces, this is no longer true. You can allow self-intersections as illustrated by this example. Another interesting example, for instance, are these tori, these J-holomorphic tori that appear when considering this lattice that appears here in this picture. So here this will be a fundamental domain for the lattice, giving you this tori. Also for S3 cross S3, we have a tori like those, which is now given by this lattice spanned by these directions here in the complex plane. Okay, so this will be the classification of totally geodesic submanifolds in Merli-Kähler homogeneous six manifolds. And now let me talk a little bit about cones. So yeah, in this work we also studied totally geodesic submanifolds in Riemannian cones over a general Riemannian manifold. Well, maybe analytic. I am going to assume that the Riemannian manifold is analytic. And yeah, so when you have an immersion, a totally geodesic immersion, then you can induce a totally geodesic immersion in the cone, and vice versa. If your induced immersion is totally geodesic in the cone, this means that your links are totally geodesic. Okay. So we provide the following structured results that allow us to understand totally geodesic immersions in Riemannian cones. When we have a totally geodesic immersion in a cone, then we fall in one of the following two possibilities. It is either a cone over a totally geodesic submanifold of the initial ambient space M, or it's a totally geodesic hypersurface inside a totally geodesic cone induced by a totally geodesic immersion of the link of the cone. So we have these two possibilities. Let me rephrase it in the maximal case. So now I am considering maximal totally geodesic immersions. I think I didn't say this, but by maximal I mean that there is no other totally geodesic submanifold in between. So they are not contained in any other proper totally geodesic submanifold. So if we have a maximal totally geodesic immersion in the cone, then we have two types of totally geodesic immersions. We have those which are induced by maximal totally geodesic immersions in the link, and those are always tangent to the radial or to the cone vector field. And we have totally geodesic hypersurfaces that are not tangent, or for which the radial direction or the cone vector field is not tangent to the totally geodesic immersion. And I call them type 2, at least for the purposes of this talk. And let me say that these sort of examples, non-trivial examples, because they can arise they can arise in this process of taking cones, they actually happen. So for instance, if we take a round sphere and now we take the cone over the round sphere, this is going to be isometric to a flat space. And in a flat space, we can consider an affine subspace that does not pass through the origin, okay? And this will give us a totally geodesic submanifold which is not tangent to the radial direction of the cone, so it's a type 2. Okay, so this is a kind of trivial example of this situation where we have these type 2 totally geodesic hypersurfaces in cones. But yeah, we first believed that this was going to be the only such example, but indeed it's not. These examples are highly non-trivial. Indeed, this is so by the following family of examples. You can consider R2, and you now consider a product of R2 with this interval, and you take some smooth functions P and Q, taking values on R. Okay, so in M3, in this manifold, I am going to consider this work product Riemannian metric, and now you can prove that every submanifold of this form is going to be totally geodesic for the cone over N3. So it's going to give you a 3-dimensional totally geodesic submanifold in a 4-dimensional cone. So as you can see here, you can take every smooth function with positive values that you want, and this will give you always a totally geodesic submanifold. So the theory of totally geodesic submanifolds in Riemannian cones is far from being trivial, because not all totally geodesic submanifolds are induced by totally geodesic submanifolds of the link of the cone. You can have some non-trivial examples appearing as totally geodesic hypersurfaces. And yeah, this is something that I think also is an interesting topic of study, how big is the class of totally geodesic submanifolds of this class in Riemannian cones, or when these totally geodesic submanifolds can occur. Okay, so something that we were thinking, right, is to study the totally geodesic submanifolds in the associated holonomy G2 cones over these nearly Kähler 6 manifolds. So a theorem by James Moroiano and Semmelmann is telling us that we don't have to care about this non-trivial totally geodesic hypersurface that could arise, because if you have an irreducible Einstein manifold with a totally geodesic hypersurface, then its holonomy must be equal to SON. So in particular, it cannot be equal to G2. So in our case, we will not have these nasty, totally geodesic hypersurfaces. And indeed, using some things that we develop in this article, we can also prove that the following types of Riemannian manifolds, as a consequence of this theorem by James Moroiano and Semmelmann, do not admit totally geodesic hypersurfaces. So Sasaki-Einstein manifolds don't admit totally geodesic hypersurfaces, nearly Kähler 6 manifolds don't admit totally geodesic hypersurfaces, and nearly parallel G2 manifolds don't admit totally geodesic hypersurfaces. But the important part is that combining our structure result for maximal totally geodesic submanifolds in cones and this theorem by James Moroiano and Semmelmann, we are able to conclude the classification of totally geodesic submanifolds in cohomogeneity 1 holonomy G2 cones by just classifying totally geodesic submanifolds in nearly Kähler homogeneous 6 manifolds. And something that we observe, and I will finish with this, is that as it's not happening with Hermitian symmetric spaces of rank greater or equal than 2, totally geodesic submanifolds are very well behaved with respect to the almost Hermitian structure in this case. They are going to be J-holomorphic if they have dimension 2, or Lagrangian if they are of dimension 3. And this also reflects on the G2 cones that are associated with these nearly Kähler 6 manifolds. In this case, maximal totally geodesic submanifolds of dimension 3 will be associative, and in dimension 4 they will be co-associative. So it's also interesting to consider how well behaved are totally geodesic submanifolds in the presence of a G2 structure. Are they going to be always associative and co-associative? As we can see in the cohomogeneity 1 picture, at least for Riemannian cones, this is going to be the case. So thank you very much for your attention. I think I should stop here.
Thank you very much, Alberto. Very nice talk. I have learned a lot of different aspects of totally geodesic submanifold. Thank you very much. Are there any questions or comments?
One question regarding the last part. Since you already did the Berger spheres, do you know if if you, instead of doing G2 manifolds, just to say co-closed G2 manifolds, if then the totally geodesic submanifolds are also co-associative, or what happens if you say you just go to closed or co-closed G2 structures?
Not really. I don't know about that. But well, in that direction, we have this theorem that abstracts the existence of totally geodesic hypersurface for nearly parallel G2 manifolds, which are close, right? But they are not co-close. They are almost co-close somehow. But this is all that I can say so far. Again, with these nearly parallel G2 manifolds, there is a relation with a spin 7 geometry, right? Because when you consider the cone over them, this gives you a manifold with holonomy spin 7. And then I will expect that the total geodesic submanifolds there will also be calibrated by the spin 7 structure. So yeah, I mean, I don't know about only close or only co-closed. I don't know. I don't know.
Yeah, I was wondering if you compared it to your results on the quaternionic Berger spheres, because I mean they have these kind of co-closed structures, G2 structures.
Yeah. Sorry, co-closed or closed? I think closed, right?
They have co-closed.
Co-closed. Aha.
Yeah.
I see. I was not aware of that. So you say that S7, so for instance, has a co-closed structure.
Yes, the entire family of scaled has co-closed structures. Yeah. Exactly. But if you have not looked into it, we can talk at some other point about it if you like.
Okay, so maybe I said it wrong. So yeah, I am aware that in S7 you have a nearly parallel G2 structure.
Exactly,
right?
that is co-closed, yes. And
that is co-closed, but it's not close, right?
It's not close, correct.
Okay. That's yeah. I think I said the other way around before. Okay, right. So yeah, in that regard, I am not sure if in that case they will be well behaved. I mean, well behaved, understanding that they will be. I don't know if saying calibrated here makes sense because the structure is not close. So
no, co-calibrate would be the way to go, sure.
Yeah, so I don't know if calibrated is the word, but I am not sure. I haven't checked. If our examples are. Wait, but I think we don't have four-dimensional examples in S7. I am not. I don't remember right now. I have to check. Sorry, I have to check.
Yeah, don't worry.
I have to check, but this can be checked in our article with almost. Yeah.
Okay.
But it's interesting to pursue that. Yeah. Thanks a lot for the question,
Thanks.
Leander.
Okay, is there any other question? Okay. If not, we thank again to Alberto,
Thank you.
and we will see in 2 weeks. Okay. Thank you.
Thank you.